The linear regression formula basically includes just a straight line equation. As you know, it is y equals a0, which is one coefficient, plus a1 times x, and this is one coefficient as well. This is the slope, and this is the intercept, we can say. And of course, because we are fitting this to a data, there will be an error, a difference between the data and the curve data. So the error between the model and observations can be calculated as the discrepancy between true value and approximate value. If you isolate this here, you will see that it is the difference between y, which are the measured or observed data, minus the curve or prediction of the curve, this value. So this is the true value, this is the approximate value. And we need to have a criteria for best fit, and it can be achieved by minimizing these errors or residuals, minimizing the sum of the residuals of residual errors for all data. So we have many data, that's why we have many errors, and we actually sum them all, as you can see here. Summing them means summing this formulation for each I is the data, x data, y, and the corresponding y is the result. Basically, we sum them all like this. But the problem here is that, let's say we have 2 points, and we use this to minimize it. Of course, there is a line passing through these 2 points, and the error is 0 and 0. That means the error is 0. So having 0 error means we minimized it. But we can minimize it by having a line like this as well, because let's say our data is here, but our curve prediction is here. So this difference is a positive e from actual negative e, because the observation is lower. But on the other side, our observation is this, but curve prediction is this. So we have a positive error. And if we sum the errors, sum error means e minus e equals 0. This line, this opposite line, which doesn't pass through at all through the actual points, is giving also 0. So minimizing the error can give this line as well, which leads us to a very wrong line. And we can have also like this, or like this, or like this. So we can have many different lines which can give 0 or minimized error value, but these are not suitable. This is suitable. So how can we find this one most suitable one? We cannot find it using this, basically, especially for two data. That's why this is not usable. So any line passing midpoint will minimize the sum of errors because the errors cancel. That's why this is not usable. So second option is, okay, we can eliminate this minus error and plus error by simply using an absolute value for the minimization. In this case, this will be positive, then e plus e becomes 2e, which means the error was not minimized for this. So it will try to reduce this to here and increase this to here so that it can have this curve. But in this scenario, if we have 4 points, then again we have problem. There are many minimized curves, especially you can see that the connection of these two and the lines in between can also be minimizing the sum of the residual errors. And this is especially a case for 4 points in data. That's why any line falling within the dashed lines will minimize the sum of the absolute values, and therefore this is not usable either. Another criterion is minimax criterion, and it minimizes the maximum distance that an individual point falls from the line. Basically, we are trying to minimize the maximum distances. But here a problem is, if we have one outlier, then it tries to minimize this as well. So basically it is like minimizing this, minimizing this, minimizing these values maybe. But this outlier can be dominant here, and there can be an option like this which is affected by the outlier so much that it is very far away from these consistent data points. Actually, we expect a linear regression like this, but this outlier is emphasized so much in this minimax criterion. So that's why this is not also usable, especially we have outliers. Maybe we can remove this outlier and fit this, that's okay. But if we want to still keep this here, normally a regression should still give this. This shouldn't be very dominant. So a single point with a large error is a problem. That's why we don't use this either. We will have another criterion. And this is ill-suited because it gives unwanted influence to an outlier. And a strategy that overcomes the shortcomings of the aforementioned approaches, the approaches in the previous slide, we said that those are not suitable. So one suitable model is that we actually sum the squares of the residuals. So we have the residuals again like this, but we have the square of it, then sum it. And this time the results show that it gives only one suitable, most suitable line that fits to the data. So it yields a unique line for a given set of data. That's why this is the best approach, and it's called least squares because we have the squares and we want to find the least value of these squared errors, and it is given as SR. So how do we find the minimization of this? Basically, this is a function now, and we just want to have the derivative of it, and you know that if the derivative of a function is 0, that point is the minimized point. That's why we will have the derivative of this for each unknown. Unknowns are a0 and a1, so we take the derivative for a0 and a1 partial derivatives. Then we have these functions, we set them equal 0, then we will have these two. This is only for instance linear regression, which has two unknowns. So we have two equations. Then we can solve this. Actually, this we can set this as well. The total a0 means n times a0. It's the same. When we write it, we have this function. We simply isolated. We move this here and move this here as well, and we have this these two sets of equations, two equations of sets, let's say. And if we want to solve this for a1, you can use Gauss elimination here as well, or try to isolate a0 and then get a1. Here we eliminated a0 and then obtained a1 as a function of the other parameters of the data. Actually, you can see we obtained this function. Once we find a1 from here, because the x and y's are known now, we substitute this a1 into the function equation, simply with the mean of the output and inputs. Put a1 here and get a0. So with these two formulations, especially these are important, we can get the a1 and a0 coefficients. Then you can have a linear regression that fits the best for the data. So let's implement this in an example in the following slide. In this slide, we have an example 13.1 for linear regression. Basically, we have a data on the right hand side, you can see with 7 data. X's are 1, 2, 3, 4, 5, 6, 7. And for these inputs, we measured, for example, this data from 0.5 to 5.5. There are 6.0 as well in between. And we want to have a straight line which fits to this data. So we can use the least squares formulation that we learned in the previous slide. So in that, if you remember, a1 was n times total xi yi minus total xi total yi divided by n total xi square minus total xi square. So this is basically the formulation that you need to know to apply the least squares regression. And also, after finding a1 from here, we will use a0 equals the mean of y minus a1 and mean of x. Okay, let's find each value or each term here using the data. So for total xi, yi, we basically multiply these and get the summation of them. Then we will have total xi, yi is equivalent to, when we sum them all after multiplication, 119.5. Of course, we have n equals 7 as well. Let's keep that here too. Then we need to have the summation of xi and summation of yi. You can see here that the summation of yi is 24. The summation of xi is, we can calculate that too from between 1 to 7. So summation of xi is actually 28 and summation of yi is 24. Okay, we found these. We will put these into here. Then also we need y and x means. We can calculate them as well. If you remember, x mean is basically the summation of them, which is 28 here, 28 divided by the number of terms, 7, which gives us 4. For y, it is the same, but the summation of y values divided by 7, 3.428571. So this is the summation of y values. Let's substitute these into a1 first. a1 is equivalent to 7 times 119.5 minus total xi is 28 times total yi is 24 divided by the n 7 times total xi square. Actually, we need to calculate this too. We forgot that. Let's write it here. Total xi2 actual square. We get the square of each data here. Square, 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 then sum them, which gives us 140. So here it is 140 minus total xi's square. So the total xi is 28 and the square of this. The result from here is 0.839287. Now we will put this here. After putting that there, a0 is basically mean is 3.428571 minus a1. Let me actually write it down. Not here. We don't have space. a0 is mean of y 3.428571 minus a1 0.839287 times x, and x mean of x is 4. We found it here, 4. So the result from here is 0.0714287. With these, the least square fit is or least square regression is just y is equivalent to a0, which is 0.0714287 plus a1 is 0.839287 times x. So this is our data regression, let's say, and we can simply put x values here to predict y values, and it will give us a straight line, and that straight line is given here. You can see the data is here from 1 to 7. These are the results. Actually, for these points, these are the data, And this linear regression gives us this line. If you want to plot this, it gives us this line. Basically, you can see for the first one, it was 0.5 in data, but it gives a little larger value. You can understand it here. If you put 1, actually it's just 0.8 plus 0.07 means 0.9 kind of. So instead of 0.5, we calculated 0.9 for the first value. And you can use this to predict intermediate values as well. For example, 1.5. You can put 1.5 here, predict y value easily. So this is this procedure is very simple. As you can see, just use A1 and A0 formulations to get the results.